Hi, good afternoon, everyone. My name is Jiao, a final year PhD student from Florida State University. Today, I'm going to present Silhouette to leverage consistency mechanism to detect bugs in persistent memory-based file systems. This work is a collaboration work between Florida State University and the University of Toronto. A persistent memory file system promises high performance, but they are prone to subtle bugs due to the out-of-order persistency. In this talk, I will explain the challenges of detecting these bugs in file systems and how Silhouette addresses them and the results we've achieved. It's challenging to detect bugs in P-memory-based file systems. First, P-memory programs are prone to bugs due to the out-of-order persistency. Second, the number of possible query scenarios grows exponentially with the number of influx stores. We call those influx stores are the stores that are not guaranteed to be persisted to the device. And suppose we have n influx stores at a fence point. There could have at most 2 to the power of n query scenarios. We name it query plane. So it's prohibitive to explore them exhaustively because of the large search space. To address this, we propose a Silhouette. It first checks whether a P-memory file system implements its consistent mechanism correctly. If so, then all stores associated with these consistent mechanisms are not reordered during testing, and which we can only focus on rest of stores and dramatically reduce the search space. So first, we're going to talk about the out-of-order persistency in P-memory programming. This slide illustrates the concept of out-of-order persistency. In this figure, we have the CPU cache, and the P-memory. Initially, there are variable A and B in the system, and both are 0 at the beginning. On the left side, we have 4 instructions. First is store A with number 2, then flush A, then we store B with number 3, and fence. So first, we store A with number 2, and the variable A in the CPU cache will be updated as 2. However, due to the incoherence between the CPU cache and the P-memory, the variable A could be either 0 or 2. It hadn't been determined. Then we are trying to flush variable A from the CPU cache to the P-memory. At this moment, however, flush doesn't guarantee variable A is persisted to P-memory. This is because the flush instruction might be reordered by either the compiler or the CPU, so it doesn't take effect immediately. Next, we update variable B with number 3. Similarly, variable B in the cache is updated, but in P-memory, it could be either 0 or 3. If a query occurs before the fence instruction, in P-memory, we have variable A is either 0 or 2, and variable B is either 0 or 3, which creates 4 possible query planes. Includes A and B are persisted, or only A is persisted, or only B is persisted, or both A and B are not persisted. Suppose we have n influx stores. It could yield at most 2 to the power of n query planes. And only the fence instruction can prevent instruction reordering and guarantees all flashed variables are persisted to P-memory. In this diagram, the fence instruction guarantees variable A is updated at 2 in P-memory. However, since B is not flashed, it still could be either 0 or 3. If we have more instructions after line 4, for example, we have store C, D, flash CD, and fence. And here, if a query occurs before line 8, before the fence, we will have 3 influx stores. We have B, C, and D. They are both influx. They are both haven't been persisted to P-memory, which could yield 8 query planes to the power of 3. So if there are influx stores, there could be n to the power of n. So how to avoid such space explosion when we reorder the influx stores? Also, this issue becomes more challenging in P-memory file systems. We observe that P-memory file systems can have up to 20 or 40 influx stores at the fence points, which could yield million or trillion of query planes. so testing them exhaustively is prohibitive. This figure shows the cumulative distribution function of influx stores in the 3 tested 5 systems. We can see that there are more than 60% of fence points has fewer than 10 influx stores. Especially for PMFS and NOVA, it's 90% of fence points has less than 10 influx stores. However, they both have the long tails, and the long tail can dominate the number of cross planes. Fortunately, we also observe that P-memory file systems use well-known quasi-consistent mechanisms, such like journaling, to guarantee the atomicity and durability of operations. Also, and the real vulnerabilities lies in stores that are not associated with any quasi-consistent mechanisms. We call it unprotected stores. And these unprotected stores are fewer than 10 in our observation, and which can only have 1,000 of cross planes generated. So here, we updated the figure with the unprotected stores. The dotted line shows the unprotected stores. It shows that at most 95% of fence points had fewer than 5 influx stores, which eliminates the long tails. And meanwhile, with 10 influx stores, we still need to test 1,000 cross planes. Can we further reduce this number? By studying P-memory programs, we observe that P-memory programs often use one critical store to indicate the consistency of n influx stores, such as flag, atomic variables, epochs. So if the critical store is not ordered with respect to other influx stores, it might be a bug. However, the issue is that we don't know whether a store is a critical store. So we have a heuristic that we simply assume each unprotected store could be this critical store and test only 2 cross planes for it. First, we persist only this unprotected store and leave other stores unpersisted. Second, we persist all other stores but leave this unprotected store unpersisted. So with this heuristic, we reduce the search space. So for example, with n influx stores, a traditional combinatorial approach will generate 2 to the power of n cross planes, but our heuristic approach generates only 2 n cross planes, which dramatically reduces the search space. Based on these observations and studies, we proposed SILOE. The key ideas are detecting quasi-consistent mechanisms and checks their invariance to ensure the associated stores are also quasi-consistent with respect to reordering. Then we use the heuristic to test unprotected stores. But here we still have some challenges. So first, how to define the invariance of quasi-consistent mechanisms, how to check this invariance. The more details are in the paper, so we just briefly introduce them here. So quasi-consistent mechanisms are well defined and ordered right in multiple phases. Take an undo journal as example. The right figure is a generic undo journal in P-memory file systems. It has a header and a tail pointer to indicate the logging space. And both journal and block are in P-memory. The first phase is the log space allocation. The journal simply moves the tail pointer to indicate the allocated space. Then it uses the flattened fence instruction to guarantee the persistency of the pointer. Second phase, the undo journal logs all the data because it's all undo journal, so it logs all the data to the allocated space. Then flatten the fence to ensure the persistency. Also, sometimes they have the commit write to indicate these logging rights have been persisted. In the third phase, it conducts the in-place updates, which writes new data to the final destination address to make this and make them persisted. And last, it moves the header to the header pointer points to the tail to reclaim logs to complete or to commit this transaction. With these clear phases, we define 3 consistency invariants for this undo journal. So it includes the ordering invariance that phases must persist in sequence, which means the persist time of writes in one phase cannot be must precede the update time of the writes in the next phase. And the location invariance, logs must stay within valid regions, indicating log space is allocated within the valid journal area. And the log writes are performed within the allocated space between the header and the tail pointers. And the last one is data invariance, which means logged writes must match the in-place update because they are one-to-one matched. We log it, that we in-place update it. CLOE will check stores based on these invariants and report warnings if any checks failed. Due to a time limit, we briefly describe this how to check consistent invariants. The steps are, so first, we use LLVM paths to instrument the file system source code so that we can dynamically trace instructions, and we support the fine-grained tracing. We can see any instructions there. And then we take stores in the dynamic trace with the data type. The data type means what's the structure name, what's the structure field's name. Next, we use a lightweight annotation to determine the stores associated with consistent mechanisms. Next, we apply invariant checking on these associated stores. If invariant checks passed, then we mark this store as protected. And the rest of stores are the unprotected store. This table shows the annotation for PMFS undo journal. The first column is the attribute and metadata of the undo journal, such as a header pointer, a tail pointer, a destination address, and size that will be logged in the logging space. The second column is the structure fields that correspond to these attributes. In PMFS, the header points are computed by the base address plus the header address. Also, the tail pointer is the base address plus the tail address, a tail variable. And the destination address and size are stored in one variable. Why we say the annotation is lightweight? Because it doesn't require the source code annotation modifications. It just acts as a configuration file. And it only needs the structure name and the field to specify with respect to the metadata. And it supports simple or arithmetic operations and only require less than 10 lines per structure in our systems. We implemented CLOE in C++ and Python, and we tested 3 file systems, PMFS, Nova, and WinFS. The test ran on QEMU VMs in a their machine, and the PMemory device is emulated via the kernel command line. With the workload generated by SE, Sequence 1, Sequence 2, and Sequence 3, and some custom test cases. We compared CLOE with Winter and Chipmunk. Winter reorders stores that are read during recovery to reduce the search space. And the Chipmunk uses keyperf to trace centralized flash functions and reorder them using a combinatorial approach. And our CLOE is open source on GitHub. We tested these 3 PMemory file systems and found 15 new bugs. For example, in Nova, an incorrect pointer persistency causes the segmentation fault. Another bug in Nova causes data leaks since the truncated function is not atomic. And the data loss in PMemoryFS and WinFS due to reusing inodes in the orphan list. The full details of bug report and reproduction steps are on our repository. We also evaluated the scalability of CLOE. This graph compares the bug finding time of CLOE, Chipmunk, and Winter. With the SAE Sequence 3 workload, CLOE found more bugs in less time compared to other 2 schemes. This is contributed to CLOE's fine-grained tracing, mechanism detection, heuristic approach, and the new framework, which makes it faster and more effective. Here is the table. We also compared the number of quest planes generated by CLOE, Winter, and Chipmunk. And this number shows that Silhouette produce orders of magnitude fewer cross planes than winter chipmunk. So by focusing on unprotected stores, we reduce the overhead without sacrificing bug finding power. In summary, Silhouette is a novel tool designed to detect bugs in memory-based file systems by leveraging consistent mechanisms. It checks the implementation of consistent mechanisms. It reorders stores not associated with these consistent mechanisms and further reduce the bug search space with the 2-CPU heuristic. Silhouette is efficient, scalable, and outperformed existing approach and found 15 new bugs with 10 times speed up. And we are open source to GitHub. Thank you for listening. This is all my presentation. Any questions?